Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. Welcome to my class. So, my class is today's topic is three-phase induction motor. So, we are doing for the last few days, we are doing this chapter. So, let us see for today what are the topics that we are going to cover. So, let us check. Yes. So in three-phase induction motor, so the contents are frequency of rotor, rotor EMF, rotor current and power factor related problems. So just giving you an idea that three-phase induction motor. So in the previous classes what we have done, just briefing you that in three-phase induction motor we have done the constructional part. There we have seen the stator, there we have seen the rotor, and we have seen the two types of rotors are there, squirrel cage, and there is a slip ring induction motors are there. And then we have seen that there is a generation of rotating magnetic field. That means, so it is a motor. Induction motor is a motor. So that means in this motor we are giving electrical energy as input and we are taking mechanical energy as output. So a three-phase supply, AC supply, is given to the three-phase induction motor at the stator part. So in the stator part we have field winding. So it is energized and it is three phases are generating three magnetic field. The combination of these three magnetic field generates a rotating magnetic field, and due to which, if we place a rotor inside this stator section, the rotor faces some forces, and due to that it starts rotating. That's why this three-phase induction motor is a self-starting motor. In the previous class also, when we have discussed about the rotating magnetic fields and its nature, its characteristics, so there we have discussed that when this that this rotating magnetic field has is rotating, so it has some speed. So that speed is denoted by synchronous speed, and always in case of induction motor the rotor speed is always less than the synchronous speed. So basically whatever speed that is the mechanical output we can observe from our eyes, that speed is actually the rotor speed. Okay, but the synchronous speed, the flux speed, it is not visible to us. So it only can be calculated from the mathematical formula, and the rotor speed can be measured. It is a mechanical one. So when there is that means when due to the action of rotating magnetic field there is a flux cutting in the rotor bars, and there is EMF generation, and due to that there is a torque generation, and due to that it is rotating. So that means there also some EMF is induced, so it has some EMF value, it has some frequency value. So it's differ from the status section. That means whatever frequency we are giving as input to the system, it is not remaining as constant, it is changing in the rotor side, because the reason behind is that there is a relative speed between this synchronous speed, that the speed of the flux, and the speed of this in the rotor of the induction motor. So those things we are going to cover today, and related problem that we will do. Rotor EMF, how much EMF is induced, that equation, what is the relation, the new term we are going to learn today, that is the sleep, concept of sleep, what is the relation with sleep with the frequency, with the inductive reactance, those reactance values. So those things we are, and corresponding to that in the rotor section, whatever EMF is induced, due to that, if the motor is connected to some sort of load, then there will be some current flow. So what is the current value? What is the power factor of this induction motor? So that thing we are going to observe. What is the formulas, how to derive, what to understand from those things. So those things we have to do, and at the end we will solve some problems. Okay, so these are the topics that we are going to cover today. Yes, frequency of rotor. So what is written over here? First see, assume rotor is stationary. The rotor means rotor is stationary, means the induction motor is not running condition, it is at the standstill condition. Standstill means the rotor is not rotating. Okay, so assume the first condition is that assume rotor is stationary. So when the rotor is not rotating, that means it doesn't has any rotor speed, because it is at standstill condition. So relative speed between the rotor winding and rotating magnetic field is ns. Okay, and where the supply frequency value is given by p into ns by 120. So p is the number of poles, ns is the synchronous speed, and when 120 is the phase shift length. Okay, and now the when the rotor speeds up, so when the rotor speeds up, the relative speed is given by, what is the relative speed? So as we have discussed already, that synchronous speed, that is ns, is always higher than rotor speed, that is the actual speed n. So there is a difference. So what is the relative speed? So ns minus n. So that we can see over here. So follow my pointer. So this is the ns minus nr. So rotor frequency, as we can see, in case of synchronous speed, f is given by p into ns by 120. So that means in the, this is the fs, actually the uh, uh, synchronous when the motor has a magnetic field which has a frequency of fs. So at that time, what is fr? That is the rotor frequency. What is the generated rotor frequency? That is formula is given by same as this, f is equal to p into ns by 20. So instead of ns over there, we, in case of the stator or rotor, what we are going to write, the relative speed. So same formula, p, the number of poles, that is into ns minus n, that is the relative speed, synchronous speed minus rotor speed by 120. Okay, so now we there is a slip formula. Slip is the s denoted by ns minus n by ns. So now what is slip? We have explained in the previous classes that what is slip. Slip is the percentage the relative speed between the synchronous speed and the rotor speed, and its study is very important to identify what is the condition of any three-phase induction motor. So and that is denoted by s. Okay, so that's why I follow my pointer, s is equal to ns minus n by ns. So what is ns minus n? So this ns will be multiplied with this s. So ns minus n is equal to s into ns. And again, what is ns? Ns is equal to 120 f by p. So we have plotted that value over there. Okay, so here, yes, so here we have placed the fr is equal to ns minus n is equal to s into ns, where ns is equal to s into 120 f by p. So we have placed those values over there, s into 120 f by p. So there will be 120 cancellation, there will be p cancellation. Okay, so what is the remaining part? S into f. So rotor frequency is also known as a slip frequency, that is denoted by the formula s into supply frequency. So rotor frequency is equal to slip into supply frequency. Remember always this formula, it is very important for the different mathematical problems and also for the concept. Yes, rotor EMF. So we have seen that when rotor is there, in the rotor, what is the value of what you can say, the rotor frequency. So there is a formula s into fs, that is the slip into stator frequency. Like this way we are going to find out the rotor emf. So again, two condition we have to consider. One is the standstill condition, one is the running condition. So first we are considering the standstill condition. So at standstill condition, what is written? Under standstill condition, slip is equal to 1, the relative speed is maximum, and maximum EMF induced in the rotor. Now you may ask that why slip is equal to 1. To understand that, go to the previous one. Yes, slip is equal to 1. See, we are telling that in R the rotor is at stationary condition, that means n. See, this, follow my pointers, this slip equation, this n is equal to 0. So if this n is equal to 0, so that means the equation becomes ns by ns. So it will cancel out, the value is 1. So that's why when the motor is at standstill condition, the slip value is 1. Now coming to our slide. Yes, the when the sleep is 1, so this is the maximum value it can be possible, so we can understand that. So relative speed at that time, the relative speed is maximum, ns minus n difference is the maximum. And so if the difference is maximum, so maximum EMF is induced. Okay, so let us consider E2 is the rotor induced EMF under standstill condition. Okay, so we are considering that one. Now running condition, when the motor speed increases, so relative speed increases. That means relative speed increases means now n has some value. So now that means the relative speed is not maximum, in between somewhere in maximum and minimum value. So the rotor induced EMF is going to be decreased, because when the slip is maximum, the rotor EMF is maximum. Now the slip is decreasing, so the EMF induced is also decreasing. So what is the value of rotor EMF when it is at the running condition? Correct. So follow this one. So follow my pointer. So as we can see, this E2 is directly proportional to the NS. Okay, and this is at the standstill condition obviously, and this is for the running condition. E2R, that is the rotor EMF, is directly proportional to the relative speed ns minus n. So that ns minus n. Okay, now if we divide these two equation, E2R by E2, so if we do that, that is ns minus n by ns, ns minus n by s, that is equal to s. So from that equation we can say that E2R is equal to SE2. That means this rotor, whatever EMF is induced in the rotor, that is multiplied with the that is equal to the EMF induced at standstill condition into sleep. Okay, so that means when that means we can understand that what is the importance of sleep. So for calculating each thing we need the sleep. For calculating the frequency we need sleep. For calculating the EMF we need sleep. So it is a very important term, using which we can solve different parameters, and we can understand different things in case of three-phase induction motor. So coming to the next slide. Okay, yes, this one, rotor current and rotor power factor. So as we are saying that there are two conditions, one is the standstill condition and one is the running condition. So here also we are going to see the reactance value, the impedance value, the current value, and the power factor value, those components value at standstill condition. At the same time we are going to see the same thing at the running condition. Correct. So first let us see what is written over here, very interestingly presented over here, so that a single view can give you the idea what is standstill, what is the formula for standstill condition, what is the formula for running condition. See, okay, so first it is written that R2 is the rotor resistance per phase under standstill condition, and X2 is the rotor reactance per phase under standstill condition. So this R2 and X2 value are both at standstill condition. Okay, so now what is the value formula for now we are viewing, follow my pointer, we are viewing the equation when it is at standstill condition. This is the equation at standstill condition, and the same equation, not same pattern equation at running condition. There is some little bit changes are there. Why these changes are occurring, that I am going to tell. So X2 is the reactance. So what is the reactance formula? In AC fundamental chapter we have done this, 2 pi FL. Okay, so X2 is equal to 2 pi F into N2, where this F is the supply frequency, because there is no generation of rotor frequency, because the rotor is at standstill condition. Clear? Okay, so this is X2 is equal to 2 pi Fs into L2. Fs is equal to whatever you can mention, that is F. Okay, ohm per phase. Okay, so Z is equal to under root R2 square into X2 square. So rotor current is equal to, very simple, E2 we have considered the EMF at standstill condition. In the previous slide we have considered by Z2 the impedance of the circuit, and power factor we know that R by Z, so R2 by Z2. So these are the equations in at standstill condition. Now coming to the next condition. So in the next condition, so now in case of when we are considering rotor, so rotor, what is the value of rotor frequency, what is the value of rotor EMF, what is the value of rotor reactance? See, it is changing. How it is changing? See, already in the previous slide we have derived this. So rotor frequency is given by S into F, where F is the supply frequency, E2R is the rotor EMF is equal to at running condition is equal to S into E2, where E2 is the EMF at standstill condition, and X2R is equal to S into X2. The same way as we have derived the other components here also, we can derive this one also. Okay, so what is now impedance? Z2R is equal to under root R square plus a S x2 whole square, because now this reactance, when it is at running condition, the reactance is X2R, and X2R is equal to S into X2. So we have plotted that S into X2 in the equation. So, and rotor current I2R is equal to definitely S into E2 by Z2R. So I follow my pointer, this I2R is equal to S into E2 by Z2R. So where Z2R is equal to this component we have placed over there, and the power factor again cos 2R is equal to R2 by Z2R. So again R2 by Z2R is given by under root R square plus Sx2 whole square. So these are the equations at standstill condition and at running condition. Yes. Now coming to the problem. So what we can see over there, a three-phase induction motor is supplied at 50 Hz and is wound for 4 poles. Calculate the synchronous speed. A speed when slip is 3%, frequency of the rotor EMF when it runs at 120 mm. So very carefully think which values are given and what things we have to find out. Yes, so what values are given? So it is told that through the induction motor the supply frequency is 50 Hz. So that means F is given, correct? So and it is wound for 4 poles. So P is given, F is given, P is given. Okay, so if it is given, so what is the value of synchronous speed? What is the synchronous speed? Synchronous speed, what is the formula? See, follow my pointer. What is synchronous speed? Ns is equal to 120 F by P. F is given in the problem 50 Hz. P is also given 4. So if we put the value, we can find out the answer. So 120 into 50 by 4. So it is coming at the end. Ns is equal to 1500 RPM. Correct? Okay. So speed when sleep is 3%. So when sleep is 3%, at that time we have to find out the speed of the induction motor. Speed means the rotor speed, that means N we want to find out. So we know what formula we going to use. So already we have done the formula of sleep. What is the sleep formula? S is equal to Ns minus N by Ns. Now in the problem S is given 3%, okay, and Ns already we have calculated 1500 RPM. So what is unknown in the equation? N. So if we put the value in the equation, see here, follow my pointer, N is equal to Ns into 1 minus S. So Ns already calculated, S is given in the problem. So if we put the value, obviously when we are putting the value of S, we have to eliminate this percentage. So that means 3 by 100 we have to do, and then we can find out the rotor speed, actual rotor speed. Okay, and last one is the frequency of the rotor EMF when it runs at 1200 RPM. That means frequency of the rotor, that means Fr we have to find out. So what is the formula for Fr? That is S into F. So S is given 3%, F is what? 50. So if we multiply, then we will get 10 Hz answer. Okay, so this is the problem number 1. Coming to the next, so this is the problem number 2. So the frequency of EMF in the stator of a 4-pole 3-phase induction motor is 50 Hz, and that in the rotor is 1.5 Hz. So find out the sleep, the speed of the rotor. So first thing we have to find out the sleep, correct, and the speed of the motor. So now to find out those, just check which values are given. It is told that it is a 4-pole machine. It is told that it has a supply frequency of 50 Hz. That means initially we can find out the NS. NS formula is given by 120 F by P. But F is the 50 Hz and P is the number of pole, that is 4 is given. So first we can find out this NS, that is 1500 RPM again, and then if it is known and how to find out the sleep, so see, stator flux frequency is given 50 Hz. At the same time Fr, that is the rotor frequency, that value is also given. What is the value? 1.5 Hz. So and we know the formula Fr is equal to S into Fs. See, follow this one. S Fr is equal to, already we know that, S into Fs. Now, so what is S? S is equal to Fr by F. So Fr is known, this F is known. So Fr is 1.5 and F is 50. So if we divide, we will get the slip value, that is 0.03. Okay, if we convert this into the percentage, we will get the 3%. Okay, and so now we know the ns, we know the slip. So can we find out the speed of the motor? Yes, we can find out. The same formula, n is equal to ns into 1 minus s. So if we put the value, every values are known, so if we put the values, we can find out the answer. Okay, coming to the next. Yes, so now what is there, for a 4-pole 3-phase 50 Hz induction motor, ratio of stator to rotor turn is 3. On a certain load, its speed is observed to be 1450 rpm. So if in any problem, okay, first let me complete the problem, then I am going to discuss. When connected to 415 volt supply, calculate frequency of the rotor EMF in running condition, FR, that means you have to calculate magnitude of the induced EMF in the rotor at standstill, magnitude of the induced EMF in the rotor under running condition, assume star connected stator. Okay, very interesting problem this one. So follow my pointer. So what are the values given? Pole given, P is equal to 4. Frequency is given, supply frequency, this one is actually 50 hertz. Okay, and there is a supply voltage is given 415 volt. Okay, for stator side line voltage is given, and turns ratio is given, the motor ratio is given, stator to rotor turns, that is equal to 3. So K is equal to, actually the formula is opposite, rotor turns by stator turns, that is 1 by 3, so 0.33, and n is given, this speed is actually the rotor speed. Of in any problem, if the speed is given, that definitely we have to understand that value is actually of rotor speed. So always this speed is always given, never ns is given, and ns always we have to calculate. So okay, um, yes, so first thing we have to find out this uh, frequency of the rotor. So how to find out the frequency of the rotor? So see, so key is, that key is given for you. So ns is equal to 120 f by p. So frequency is given, what is the frequency? 50 hertz. Pole is given, that is 4. So we can find out that ns is equal to 1500 rpm. So ns is given, n is given in the problem, so 1450, so 1500. So here ns, follow my pointer, ns is 1500, n is 1450 by 1500, we will get some answer, that is the sleep value. Okay, so now fr, we can, the first thing we can have the frequency of the rotor EMF, that fr is, we have to find out. So fr is equal to sleep into f is given 50, and s we have calculated from here. So putting that, we can find out fr. So first solution is there. Okay, and next one is the magnitude of the induced EMF in the rotor at standstill. So what is the EMF at standstill? So here the K is formula is given by, as you can see over there, EMF of the secondary side rotor side phase voltage and stator side phase voltage is equal to, you know the formula, the rotor turns by stator turns. Now see, we have just placed the value. So stator side per phase voltage is given, that is equal to line voltage, that is given EIL by root 3. So here EIL in the problem it is given 415 by root 3, because we are converting the line voltage into phase voltage, and we know that from line and phase voltage there is a relation, VL is equal to root 3 of V phase, we know. So V phase is equal to VL by root 3. So that equation we have used over here to find out the phase voltages. Okay, so this is the phase voltages, and now in the rotor side, what is the EMF induced? So at standstill, this is the voltage value. Okay, and at running condition, that value will be multiplied with the sleep, and that value will give us the running condition EMF value. Okay, so this is very interesting. So this kind of problem you have to solve. Okay, yes. Now this is another problem. A 4-pole 3-phase 50 Hz induction motor has a star connected rotor. The rotor has a resistance of zero point 0.1 ohm per phase and standstill reactance of 2 ohm per phase. The induced EMF between the slip ring is 100 volt. If full load speed is 1460 and RPM, find slip, rotor frequency, rotor current, power factor on full load condition. Assume slip rings are shorted. Okay, so first, as I have always told students, that first see which values are given, and then check what we have to find out. So first thing is that poles is given, P is equal to 4, and then 50 hertz is the supply frequency. Rotor resistance is given per phase, that is zero point 0.1 ohm. Rotor reactance is given 20 ohm per phase. E2 is given, that is the air gap voltage is given, that is 100 volt, and the rotor speed n is given 1460. Okay, so now just we have to sleep we have to find out. So what is the sleep formula? That is ns minus n by ns. So n is given in the problem 1460. So follow my pointer here, n is given, that is 1460. Now we have to just find out the ns. So ns formula is 120 f by p. F is given, p is given, again find out this, and for the plot put that value over here, and you get the sleep. So first result is then rotor frequency. What is the rotor frequency formula? Fr is equal to s into f. So s already we have calculated, and f is given in the problem, so we can find out that one. So rotor current, so rotor current formula is given, this one, I2R is equal to AC2 by under root R2 square plus SX2 whole square. So now all values are given in the problem, so just put the value, you can find out the current value. And the cos phi 2R is again, we know the R2 by Z2, where Z2 is equal to under root R2 square plus SX2 whole square. So if all values are given, so just put the values, and you can find out you can find out your solution. So these are the different types of problems we have to deal with in the semester. Okay, so not I'm not going for this problem also, just note it down. But you can yourself, you have to do. I have already solved 4 problems. This is your part, so you just try. I have given some key here, so you just try at home to how to solve this kind of problems. Okay, so this is problem number 6 is also there, you can try this at home. Problem number 7, 8, 9. So these are the lots of problems I have given over here for you. So just 4 5 problems you just listen of mine, and then the rest of the problem that I am not discussing with you. So it is left to you for the solution. Just you yourself check and try to solve those problems. Okay, it will be very helpful to you, that uh, you will able to solve any kind of three-phase induction, sleep and rotor frequency, rotor current, though that kind of problems. Okay, so this is all for today. So I think now you are able to solve this your level problems of three-phase induction motor. So this is for all for today. Thank you.